Hey, welcome to the Explainer. Today, we're talking about one of the most important, yet most overlooked components in all of electronics. I'm talking about capacitors. Seriously, they are everywhere. Your phone, your computer, you name it. They're the unsung heroes, and by the end of this, you are going to have a whole new appreciation for them. So, here's our game plan. We're going to start with the absolute basics, what a capacitor even is. Then we'll get into what capacitance means. From there, we'll pretend we're engineers and figure out how to design one, see how they play together in circuits, and then, my favorite part, we'll run through some real-world examples to make it all click. Let's do it! Okay, so, Section 1, what is a capacitor? Before we get into the nuts and bolts, let's start with a little mystery that you've probably seen 100 times. Right? Think about it. Your phone's battery is totally, completely dead, 0%. But you hit the power button, and somehow it finds just enough juice to flash that "please charge me" screen. Where does that last little gasp of energy come from? The secret is the capacitor. It's a tiny little device that holds on to a small charge and can release it in an instant. Don't think of it like a battery, which gives you a slow, steady stream of power. It's more like a camera flash, a quick, intense burst right when you need. So what is this thing really? Well, at its heart, a capacitor is shockingly simple. It's just two metal plates, really close together, but, and this is key, they never touch. In between them is an insulator, a material we call a dielectric. When you hook it up to a battery, electrons get crammed onto one plate and pulled off the other. This creates an electric field between them, and that field is where the energy is stored. The circuit symbol makes perfect sense too. It's just two parallel lines. Just don't get it mixed up with a battery symbol. That one has lines of different lengths. All right, so capacitors store charge. The obvious next question is, well, how much can they store? And that brings us to the whole idea of capacitance. When physicists ran experiments on this, they found something really cool and really consistent. If you plot the amount of charge stored, we call that Q, against the voltage you apply, that's V, you get this, a perfect straight line. What does that tell us? It means the charge you can store is directly proportional to the voltage you put in. Double the volts, you get double the charge. Simple as that. This perfect relationship gives us our definition. We say that capacitance, which we write with a capital C, is just the ratio of the charge stored to the voltage you applied. And that gives us this fundamental formula, C equals Q over V. For any one capacitor, this value, its capacitance, is always constant. We measure capacitance in a unit called the Farad, named for the great Michael Faraday. 1 farad is 1 coulomb of charge per volt. Now, here's the thing you have to know. 1 farad is huge, like impractically huge. You'll almost never see a 1 farad capacitor in the wild. Instead, we're always dealing with tiny fractions, like microfarads or even nanofarads. Okay, let's put on our engineering hats. If we wanted to build a capacitor from scratch, what parts of it could we change to make it store more or less charge? Let's check out the blueprint. Turns out there are really only 3 big things you can tweak to control a capacitor's capacitance. Number 1, the area of those metal plates. Number 2, how far apart they are. And number 3, the real secret sauce, the type of insulator you stick between them. The first 2 are pretty intuitive, right? If you have bigger plates, there's just more surface area to pack electrons onto, so you get higher capacitance. And if you bring those plates closer together, the attraction between the positive and negative charges gets way stronger, which also bumps up the capacitance. I mean, if one plate was in LA and the other was in New York, they're not going to affect each other at all. Now for that third factor, the dielectric. This is the game changer. Just by putting some kind of insulating material in that gap instead of empty space, you can seriously crank up the capacitance. And the specific material matters a lot. We measure this effect with something called relative permittivity. A vacuum is our baseline at 1. Air barely changes anything. But look down this list. If you use something like barium titanate as your insulator, you can increase the capacitance by a factor of 1,200. This is how we get so much power into such tiny little components. So let's put all that together. This is it, the master recipe for a parallel plate capacitor. The capacitance C is just a function of the material you use, the area of your plates, and the distance between them. This single formula is behind the design of countless electronic components. Now, in a real electronic device, you almost never find a capacitor all by its lonesome. They're team players. And they can team up in two fundamental ways, what we call series or parallel. So on the left here, you see capacitors in series. They're lined up one after the other, like train cars. On the right, they're in parallel, where they're connected side by side. And how you wire them up totally changes how they behave as a group.
Now here's a fun twist. If you know about combining resistors, the rules for capacitors are the exact opposite. When you put them in parallel, you just add their capacitances together. It makes sense, right? It's like you're just making one big capacitor with a larger total plate area. But when you put them in series, you have to add the reciprocals. And the weird result is that the total capacitance is always less than even your smallest capacitor in the chain.
All right, enough theory. Let's get our hands dirty and actually apply these rules. This is where you see how all these formulas work in the real world. Ready? Let's run some numbers. So let's look at designing two different types. For a classic parallel plate capacitor, we can just plug its size and spacing into our blueprint formula to get its capacitance. In this case, about 0.8 nanofarads. But what if the capacitor is a sphere? The geometry is different, so we derive a whole new formula for it. The big takeaway here is that a capacitor's capacitance is purely defined by its physical shape and size.
Now let's try combining them. First, a parallel circuit. The rule is super easy. Just add them up. 50 plus 10 gives us 60 microfarads total. Done. For the series circuit, we use that funky reciprocal rule. And when you run the math, the total comes out to just 4 microfarads. See? The total for parallel is bigger, and the total for series is smaller, just like we said.
This is a really cool one, charge sharing. Imagine you charge up a capacitor to 6 volts. Then you connect it to another identical capacitor that's completely empty. What do you think happens? Well, that initial charge has to spread out across both of them now. Since the total capacitance has doubled, but the total charge stayed the same, the voltage gets cut exactly in half. It drops to 3 volts. We've covered a ton of ground, but now we're at the most important question. So what? Why do we care? It all comes down to energy. A capacitor's entire job is to store and release energy fast. And we can actually calculate exactly how much energy, or U, it's holding, with formulas like 1/2 CV squared. This lets us measure the punch that these little guys are packing. You know, from the flash on your camera, to the circuits that tune your radio, to that last-ditch warning on your dead phone, capacitors are what make it all happen. They are these tiny, perfect reservoirs of energy, ready to be filled and emptied millions of times a second. And that simple, powerful ability, well, it's what makes our entire digital world tick.